two machines built with 69 kilobytes of memory are falling through the void between stars at 38,000 miles per hour. They have been out there for nearly 50 years. The nearest star is still 40,000 years away. Every year, 4 more watts of power drain from their dying nuclear hearts, and the instruments go dark one by one. Soon, the last whisper will fade, and humanity will have nothing left out there at all. What the Voyagers found on their way out of the solar system rewrites everything we thought we knew, and what waits beyond it is stranger than anyone predicted. If you enjoy this kind of journey, hit subscribe and stay with us. We begin now. In the summer of 1977, an alignment was taking shape that had not occurred since Thomas Jefferson was alive. Jupiter, Saturn, Uranus, and Neptune were drifting into a configuration that would allow a single spacecraft, if launched at precisely the right moment, to use the gravity of one planet to reach the next, a slingshot chain across the entire outer solar system. The alignment would hold for just a few years, and then the planets would scatter back into their separate orbits. The next opportunity would not arrive for 176 years. The National Aeronautics and Space Administration had been planning for this window for nearly a decade. The original concept was called the Grand Tour, an ambitious 4-planet mission that Congress ultimately slashed for budget reasons. What survived was a leaner, cheaper pair of spacecraft called Voyager. The official mission called for flybys of Jupiter and Saturn only. 4 years of operation. Anything beyond that was a bonus no one was willing to guarantee. Voyager 2 launched first, on August 20th, from Cape Canaveral, Florida. Voyager 1 followed 16 days later, on September 5th, riding a faster trajectory that would allow it to overtake its twin within months. By December, Voyager 1 had already pulled ahead. Both spacecraft were smaller than a compact car, each weighing roughly 815 kilograms. Their bodies were wrapped in thermal blankets, their arms extended with instruments designed to taste and measure and listen to everything they passed through. The engineers who built them at the Jet Propulsion Laboratory in Pasadena, California, understood something the public did not. These machines were fragile. Each one carried 10 scientific instruments, including cameras, magnetometers, spectrometers, cosmic ray detectors, and plasma wave antennas, all of which had to function perfectly in conditions that would destroy most consumer electronics within minutes. Their systems were designed for a 4-year mission in the unforgiving vacuum of deep space, where temperatures swing between searing heat and absolute cold depending on orientation, where radiation bombardment degrades circuitry, and where a single component failure could end everything. Redundancy was built into every critical system, because at the distances Voyager would travel, no repair crew was coming. Every bolt, every circuit, every line of code had to work the first time. The margin for error was essentially zero. The political context of the launch matters. The Grand Tour had been proposed in the late 1960s as a once-in-a-lifetime opportunity to visit all 4 outer planets in a single mission arc. Congress looked at the price tag and flinched. The full Grand Tour was cancelled. What NASA managed to salvage was a stripped-down version, 2 spacecraft aimed at Jupiter and Saturn only, with the possibility of extending the mission to the ice giants if things went well and if the spacecraft survived. The Voyager program cost roughly $865 million, a fraction of what the Grand Tour would have required. Adjusted for inflation, the entire mission that would eventually become the farthest-reaching exploration in human history cost less than many single Earth-orbiting satellites built decades later. Nobody involved in the launch imagined what would actually happen. The 4-year mission would stretch across 5 decades. The instruments designed for planetary flybys would be repurposed to explore regions of space no human technology had ever reached. And the 2 small machines tumbling away from Earth would become the farthest objects humanity had ever created, still transmitting faint signals from the darkness between the stars nearly 50 years later. Nobody imagined them reaching the boundaries of interstellar space. Nobody imagined them outliving the engineers who built them, the scientists who designed their instruments, or the political leaders who approved their budgets. The Voyager program was supposed to be a quick look at the outer planets, a scientific expedition wrapped up before the decade was out. What it became instead is the longest, farthest, and most improbable journey of exploration in the history of the species. That story begins with the machines themselves, and a set of engineering decisions that should not have worked for this long. Take a modern smartphone and strip away everything except a sliver of its memory. Divide what remains by 3 million. That is how much computing power each Voyager carries. 69 kilobytes of onboard memory, an 8-track tape recorder for storing science data, processors that run at a fraction of the speed of a basic calculator you could buy at a drugstore. The transmitter that sends data back to Earth operates at 23 watts. A standard refrigerator light bulb draws more power than that. From Voyager 1's current distance of over 15 billion miles, the signal that reaches the 70-meter dishes of the Deep Space Network is so unimaginably faint that it would take 20 million years of continuous reception to collect enough energy to power a single household light for 1 second. The engineers at the Jet Propulsion Laboratory in Pasadena built a detection system sensitive enough to pluck that whisper out of the noise of the entire galaxy. Everything about the Voyagers was built with the technology available in the early 1970s. The computers were programmed in languages that have since been abandoned. The storage media are formats that no longer exist on Earth. Several of the original engineers have retired or passed away, and NASA has had to recruit retired specialists just to maintain communication protocols that modern systems were never designed to handle. There is no user manual for these spacecraft. The institutional knowledge lives in the memories of people who were young when the machines launched, and who are now approaching the end of their own careers. Yet both spacecraft are still functioning. Voyager 1 has been operating continuously for nearly 49 years. Its systems have survived temperature extremes, radiation bombardment, micrometeorite impacts, and the gradual decay of their own power sources. In 2017, NASA successfully fired Voyager 1's backup trajectory correction thrusters for the first time since 1980. The thrusters had sat dormant for 37 years in the cold of deep space, and they worked on the first attempt. The scan platform, which aims the cameras and instruments, jammed on both spacecraft at different points during their planetary encounters. Voyager 1's stuck in 1978, Voyager 2's jammed during its closest approach to Saturn, threatening to destroy the entire encounter's science return. Both times, engineers on Earth found workarounds, sending commands that took hours to arrive, adjusting the spacecraft's orientation to compensate for hardware that had locked in place. This is what kept humanity's eyes open at the edge of the solar system. Machines built before the personal computer existed, running on less power than a dim light bulb, held together by engineering intuition, meticulous redundancy, and a measure of luck that their own creators fully expected to expire decades ago. The fact that both spacecraft are still transmitting is either an extraordinary testament to conservative design or the longest sustained lucky streak in the history of technology. Bolted to the side of each Voyager is a gold-plated copper phonograph record, 12 inches in diameter, encased in a protective aluminum jacket. A cartridge and needle are included. Etched into the cover are instructions, rendered in symbolic language, explaining how the record should be played and where in the galaxy the spacecraft came from. 14 pulsars are mapped on the surface, each one identified by its unique rotational period, so that any civilization capable of reading the diagram could triangulate the position of our star within the Milky Way. The contents were selected by a committee chaired by Carl Sagan, the planetary scientist and author who would later become one of the most recognized voices in science. Sagan understood that the Voyagers, once they left the solar system, would drift through interstellar space for hundreds of millions of years, the records needed to survive that timescale. Gold does not corrode in vacuum. The etchings will remain legible long after every structure on Earth has turned to dust. 115 images are encoded in analog form on each record, using a system that translates visual information into audio waveforms that can be played back and reconstructed by any civilization that understands the instructions on the cover. The images show human beings in various stages of life, from infancy to old age. They show the structure of DNA. They show continental drift, the chemical composition of Earth's atmosphere, a woman nursing a child, a diagram of the solar system with the spacecraft's trajectory marked, mathematical definitions, starting from basic arithmetic and building to more complex concepts, photographs of cities and landscapes, and animals and insects and flowers. Following the images, the audio portion begins with spoken greetings in 55 languages, starting with Akkadian, a language spoken in ancient Sumer roughly 6,000 years ago, and ending with Wu, a modern Chinese dialect. A child's voice says hello in English. A woman offers greetings in Mandarin. Voices in Arabic, Hindi, Bengali, and dozens of others take their turns, each greeting lasting only seconds. After the greetings come the sounds of Earth, surf breaking on a shore, wind moving through trees, thunder rolling across a plain, birdsong, whale calls, the cry of a baby, a mother's first words to her newborn, and then 90 minutes of music, chosen to represent the full range of human expression. A selection of Bach, Beethoven, and Mozart, alongside Javanese gamelan, Senegalese percussion, a Navajo night chant, and Chuck Berry's Johnny B. Good. The probability that any intelligence will ever encounter either Voyager and play the record is so close to zero that it barely registers as a number. Neither spacecraft is aimed at a nearby star. The void between stellar systems is so vast that the Voyagers could drift for billions of years without passing close enough to anything for the record to be found. Sagan knew this. The committee knew it. They built it anyway. The launching of this bottle into the cosmic ocean, Sagan wrote, says something very hopeful about life on this planet. The golden record was never really a message to aliens. It was a message to ourselves. A declaration that even when facing the incomprehensible emptiness of the universe, human beings would choose to send music. A statement of identity launched into a void that does not care, carrying evidence that at least one species on one planet, for one brief moment in cosmic time, thought it was worth the effort to say we were here. The records carry one more detail that often goes unmentioned. Among the sounds encoded on the disc is a compressed recording of Anne Druyan's brainwaves, made while she meditated on the experience of falling in love. Druyan, who would later marry Sagan, had her electrical brain activity recorded and included as a 1-hour segment. It was a love letter encoded in the language of neurons, sent into the galaxy on the slim chance that someone, somewhere, might one day decode the pattern and understand what it felt like to be human and in love. The chance of that happening is functionally zero. The gesture is functionally infinite. The spacecraft carrying those golden records had a more immediate and practical purpose ahead of them, however, and Jupiter was the first stop on the itinerary. The largest planet in the solar system was waiting at a distance of roughly 500 million miles, and what the Voyagers found there would change everything. Scientists thought they knew about moons, atmospheric storms, magnetic fields, and what kind of violence a planet can produce in its own backyard. Jupiter's gravity is a weapon. The planet is so massive that its gravitational field extends millions of miles into space, bending the paths of anything that passes near it. The Voyager mission planners used that field deliberately, aiming each spacecraft at a precise point in the planet's gravity well that would accelerate the craft and redirect it toward Saturn. The principle is simple. A spacecraft falls toward a planet, picks up speed from the planet's own orbital motion, and gets flung outward faster than it arrived. A gravitational slingshot. Voyager 1 reached Jupiter on March 5, 1979, about 18 months after leaving Earth. Voyager 2 followed in July. Both spacecraft accelerated dramatically during their flybys, gaining enough velocity to reach Saturn years ahead of what their rockets alone could achieve. Without Jupiter's assist, the mission to Saturn would have required a far larger and more expensive launch vehicle. Without Saturn's subsequent assist, Voyager 2 could never have reached Uranus. Without Uranus, Neptune was impossible. Every destination in the Voyager mission depended on the one before it. Miss the gravity assist window at Jupiter by even a small margin, and the entire chain breaks. The navigation had to be precise to within a few dozen miles over distances of hundreds of millions of miles, and the engineers achieved this using computers less powerful than a modern wristwatch. The slingshot was only the mechanism. The real story at Jupiter was what the cameras revealed during those brief flybys. Dozens of interacting hurricanes, some as large as entire planets, churned through the cloud bands. The Great Red Spot, a storm astronomers had watched from Earth for over 300 years, turned out to be a swirling anticyclone of extraordinary complexity, sitting 5 miles above the surrounding clouds. Time-lapse movies assembled from Voyager images showed it pulling in smaller storms, shredding them, and incorporating their energy into its own rotation. 3 previously unknown moons appeared in the images: Thebe, Metis, and Adrastea, tiny bodies orbiting so close to Jupiter that they had been invisible from Earth. The planet's magnetic field was far stronger and more extensive than anyone had predicted, creating a radiation environment intense enough to damage the spacecraft's electronics during close approach. Everything at Jupiter was bigger, more violent, and more dangerous than the models had suggested. The radiation was particularly alarming. Jupiter's magnetic field traps charged particles from the solar wind and from Io's volcanic output, accelerating them to tremendous energies. The resulting radiation belts are the most intense of any planet in the solar system, strong enough to kill an unshielded human in minutes. Both Voyagers passed through this radiation environment during their flybys, and the bombardment of high-energy particles caused glitches in the spacecraft's electronics, scrambling data and triggering error corrections. The cameras occasionally produced garbled images. Memory cells flipped. For a few tense hours, engineers at the Jet Propulsion Laboratory were not certain the spacecraft would emerge from the radiation zone with their systems intact. They did. The thermal blankets and the shielding built into the spacecraft's most sensitive components absorbed enough of the radiation to prevent permanent damage. But the experience was a stark reminder that Jupiter is not a gentle giant. It is surrounded by a killing field of charged particles that would destroy any unprotected machine or human that ventured too close. The Voyagers survived by design, by redundancy, and by a measure of luck that the engineers preferred not to discuss publicly. And the greatest shock of the entire encounter was hiding on the surface of the innermost large moon, waiting for a navigation engineer to notice something strange at the edge of a routine photograph. Linda Morabito was a navigation engineer at the Jet Propulsion Laboratory, and her job during the Jupiter flyby was not glamorous. She processed images to determine the precise position of the spacecraft relative to Jupiter's moons, a task that required enhancing the brightness of faint objects near the edge of each frame. On March 9, 1979, she pulled up an image of Io taken by Voyager 1 4 days earlier and noticed something strange along the moon's limb. A bright, curved feature was extending from the surface, reaching hundreds of miles into space. Her first thought was that it might be another moon passing behind Io. The shape was consistent with that explanation, but when she checked the positions of all known moons, none of them were anywhere near that location. The feature was a volcanic plume, an eruption so powerful that it was launching material 300 miles above the surface of Io, visible as a glowing arc against the blackness of space. Active volcanoes had never been confirmed anywhere in the solar system except Earth. The discovery rewrote planetary science overnight because it demolished a fundamental assumption that had guided decades of research: the assumption that moons are geologically dead. What makes Io erupt is Jupiter itself. The giant planet's gravity squeezes and stretches Io's interior as the moon orbits, and the other large moons tug on it as well, preventing its orbit from becoming perfectly circular. This creates a relentless cycle of tidal heating that melts rock deep inside the moon. Io's interior is in constant turmoil, generating 100 times more volcanic activity than our own planet produces. Entire lakes of molten sulfur pool on the surface. Plumes of volcanic gas reach altitudes that would put them in the upper atmosphere of Earth if transplanted. The surface is remade every few thousand years by fresh lava flows, which is why Io has almost no impact craters. They get buried before they can accumulate. Scientists had studied our own moon for centuries and built their understanding of satellite geology around the idea of a cold, inert body shaped only by ancient impacts and slow cooling. Io shattered that framework in a single image sequence. A moon could be alive, a moon could have a molten interior, an actively resurfacing landscape, and enough volcanic power to influence its parent planet's entire magnetic environment. The implications rippled through planetary science, because if the most basic assumption about moons could be this spectacularly wrong, how many other assumptions about the outer solar system were equally mistaken? The answer, as the Voyagers would demonstrate over and over, was most of them, and the volcanic activity on Io was only the beginning of what it was doing to the space around it. The volcanoes on Io do something that nobody anticipated. They pump roughly 1 ton of sulfur and oxygen into Jupiter's magnetic field every single second. This material does not fall back to the surface. The volcanic plumes launch it high enough for Jupiter's powerful magnetosphere to capture it, and once captured, the atoms become ionized and spread into a glowing ring around the planet. Scientists named it the Io Torus, a donut-shaped cloud of ionized particles orbiting Jupiter at the same distance as Io. The torus is enormous, extending hundreds of thousands of miles through space, and it fundamentally changes the behavior of Jupiter's entire magnetic environment, Jovian system. Lightning sparked by this current blooms in the clouds above the point where the flux tube connects to Jupiter's upper atmosphere. Io, a moon roughly the size of Earth's own moon, was driving the electromagnetic weather of the largest planet in the solar system. A single volcanic body was reshaping the environment of its parent world on a scale that no scientist had imagined possible. The relationship between Io and Jupiter is one of the most extreme examples of planetary interaction ever discovered. The moon feeds the planet's magnetosphere with raw material, and the planet tears the moon's interior apart with gravitational force. It is a cycle of destruction and creation that has been running for billions of years, long before any telescope on Earth was pointed at the sky, long before any species existed that could wonder what was happening out there. The discovery forced a complete rethinking of how moons interact with their host planets, and it raised a question that would echo through the rest of the mission. If Io could be this active, this influential, this profoundly different from expectations, what else had been wrong about the assumptions scientists carried into the outer solar system? The answer was waiting on the next moon over. Voyager 1 was cruising past Jupiter's night side when its instruments picked up a radio signal with a distinctive pattern. The signal was a whistler, an electromagnetic wave generated by atmospheric lightning that spirals along magnetic field lines and drops in pitch as it travels. Scientists recognized the fingerprint immediately. Lightning. Somewhere deep in Jupiter's clouds, electrical discharges were releasing bursts of energy that dwarfed anything observed on Earth. Then the cameras confirmed it. As the spacecraft looked back at Jupiter's dark hemisphere, bright flashes of light were erupting inside the cloud layers, illuminating the tops of clouds from below. Each flash lasted only a fraction of a second, but the scale was immense. Jupiter's lightning happens deeper in the atmosphere than Earth's. at pressure levels where the temperature would crush and vaporize any terrestrial weather system. Before Voyager, lightning was considered an exclusively terrestrial phenomenon. Theories existed about its possibility on other worlds, but nobody had detected it. Voyager 1 changed that in a single flyby. The discovery proved that the basic physics of atmospheric electricity, charge separation and discharge, operates throughout the solar system wherever the conditions are right. It opened a new field of comparative atmospheric science that continues to produce discoveries today, from Saturn's lightning storms studied by Cassini to theoretical models of electrical discharges on exoplanets. Jupiter's atmosphere itself was a revelation at close range. The Great Red Spot, which astronomers had observed through telescopes for over 3 centuries, turned out to be an anticyclone of staggering complexity. The storm rotates counterclockwise, sits 5 miles above the surrounding cloud deck, and was roughly twice the size of Earth when Voyager flew past. Around the red spot, dozens of smaller hurricanes churned through the cloud bands, colliding and merging in patterns that defied atmospheric models. The banding itself, those familiar stripes visible through backyard telescopes, turned out to be a system of alternating jet streams, some blowing east and others west, with wind speeds reaching hundreds of miles per hour at the boundaries between bands. Jupiter was an engine of atmospheric violence, powered by internal heat radiated in quantities far greater than what the planet receives from the distant star. The internal heat source remains one of Jupiter's most important characteristics for understanding the outer solar system. The planet gives off nearly twice as much energy as it absorbs from external sources, meaning something inside is still generating heat, likely the slow gravitational contraction that has been occurring since the planet first formed, from the disk of gas and dust surrounding the young star 4.5 billion years ago. Jupiter is, in a sense, a failed star. It was not massive enough to ignite nuclear fusion, but it retained enough primordial heat to make its atmosphere one of the most energetic environments in the solar system. The storms, the lightning, the jet streams, and the magnetic field all trace back to this internal engine. Remove it, and Jupiter becomes a cold, quiet ball of gas. With it, the planet is a factory of weather systems, more powerful than anything else in our neighborhood, and the Voyagers captured them in detail that ground-based telescopes could never have achieved. When both Voyagers flew past Europa, the 4th largest of Jupiter's moons, the images showed something that nobody expected. The surface was almost perfectly smooth, no impact craters, no jagged mountains. Instead, the entire moon was covered in a web of dark lines, intersecting cracks that spread across the ice like veins on the back of a hand. On every other body in the solar system, craters accumulate over billions of years. A smooth surface means one thing: something is erasing them. On Europa, the answer appeared to be ice. The surface was frozen water, and the cracks suggested that the ice was moving, breaking apart, and refreezing in cycles that could only happen if something liquid existed beneath. The calculations that followed were straightforward. Europa orbits close enough to Jupiter to experience tidal heating, the same gravitational squeezing that melts Io's interior. Europa's orbit is more circular than Io's, so the heating is less intense. It melts rock on Io, but on Europa, the gentler version would be enough to maintain a liquid water ocean beneath a shell of ice, perhaps 10 to 15 miles thick. If that ocean exists, and later, missions by the Galileo spacecraft and observations from the Hubble Space Telescope confirmed strong evidence that it does, then Europa contains more liquid water than all of Earth's oceans combined. Imagine that for a moment. A moon smaller than our own, orbiting a gas giant nearly 500 million miles from the nearest warmth, holding more water than every river, lake, and ocean on the planet where life originated. An ocean that has been in continuous contact with a rocky seafloor for billions of years, warmed from below by tidal energy, shielded from the lethal radiation of Jupiter's magnetosphere by miles of ice above. On Earth, every place where liquid water touches rock and energy is available. Life exists. Hydrothermal vents at the bottom of our oceans support entire ecosystems that have never seen sunlight, powered entirely by chemical energy seeping from the planet's interior. The question Europa raised, and that remains unanswered today, is whether the same process has happened beneath its frozen shell. Could there be organisms in that dark ocean, feeding on chemical energy seeping from the rock below, completely unaware of the frozen ceiling above them, completely ignorant of the universe beyond? A mission called Europa Clipper launched in 2024 to investigate, carrying instruments designed to measure the thickness of the ice, the chemistry of material ejected through surface cracks, and any signatures of organic molecules that might hint at biological activity below. The entire mission exists because of what Voyager's cameras captured during a brief flyby more than 45 years ago. One set of photographs, taken by a spacecraft built with 1970s technology, opened a question about extraterrestrial life that an entirely new generation of scientists is now trying to answer. Before Voyager, rings were Saturn's signature. The great system of concentric bands, visible through a backyard telescope, had been part of Saturn's identity since Galileo first saw them in the 1600s. No other planet was known to have anything like them. Rings were considered a rare and beautiful anomaly. Then, Voyager 1 found thin, faint rings circling Jupiter, a planet that nobody had associated with ring systems. The discovery was modest compared to Saturn's grandeur. A few narrow bands of dust and debris, barely visible in most images. But the implications were enormous, because it meant that ring systems might be a common feature of giant planets rather than a one-of-a-kind curiosity. The idea would be tested at Uranus and Neptune in the years that followed, and both planets confirmed what Jupiter had hinted at. Every gas giant in the outer solar system carries a ring system. Each one is different. Saturn's are bright, icy, and spectacular. Jupiter's are thin and dark. Uranus has narrow, nearly invisible rings that were first detected from Earth during a stellar occultation. Neptune's rings include strange arcs that should have smeared out into uniform bands under the laws of orbital mechanics, but somehow persist. The variety was bewildering. Saturn's rings are bright, icy, and spectacular, visible from Earth with a modest telescope. Jupiter's are thin, dark, and composed primarily of fine dust particles. Uranus has narrow, nearly invisible rings that were first detected from Earth during a stellar occultation, when a distant star winked on and off as ring material passed in front of it. Neptune would later reveal its own rings, including strange arcs, incomplete ring segments that should have smeared out into uniform bands under ordinary orbital mechanics but somehow persist, held in place by the gravitational influence of nearby moons. The variety of ring structures forced scientists to develop entirely new models of how rings form, evolve, and maintain themselves. Some are ancient, dating back to the earliest days of the solar system. Others may be surprisingly young, the debris of moons that shattered or comets that wandered too close. The physics that governs each system involves gravitational resonances, tiny moonlets, electromagnetic forces, and interactions with the planet's magnetic field, all operating together in ways that are still being untangled. Every ring system discovered by Voyager told the same underlying story. The outer solar system is far more dynamic, more violent, and more structurally complex than the calm, orderly picture that telescopes had suggested from billions of miles away. The elegant rings visible through a backyard telescope were, up close, chaotic battlefields of colliding particles, sculpted by invisible gravitational forces, maintained by moons too small to see from Earth, and evolving on timescales ranging from hours to millions of years. And if the rings were more complicated than expected, the planets they encircled were about to prove far stranger still. Saturn held secrets that would keep scientists busy for decades after Voyager passed through. Saturn's rings had been a defining feature of the planet for 4 centuries. Astronomers counted fewer than 6 broad, distinct bands. The textbook picture showed a beautiful but relatively simple structure. A few concentric rings separated by gaps, made of ice and rock. Voyager obliterated that picture. When the spacecraft arrived at Saturn in 1980 and 81, the cameras revealed that each broad ring was actually composed of hundreds of individual ringlets, some so narrow they were barely resolvable. The structure was fractal in character. Zoom in on any section, and more complexity appeared. Braids twisted through the F-ring like DNA strands. Spokes, dark radial markings that rotated with the ring system, appeared and vanished in ways that defied the standard laws of orbital mechanics. Gaps that appeared empty from Earth turned out to contain faint material, while regions that appeared solid from a distance broke apart into thousands of individual strands under close inspection. Two tiny moons, Pandora and Prometheus, were discovered orbiting just inside and outside the F-ring. Their gravitational influence kept the ring confined to its narrow lane, a concept scientists named shepherding. The gravity of these small bodies sculpted the ring material the way banks contain a river, preventing it from spreading and dissipating. The concept of shepherding moons was born from these Voyager images and has since been applied to ring systems throughout the solar system. Voyager 2 flew so close to the ring plane that its instruments recorded hundreds of tiny impacts per second. Dust grains, particles shed from the rings themselves, were bombarding the spacecraft at high velocity. The team monitored the impacts with growing concern. The spacecraft survived without damage, but the experience demonstrated that ring systems are dynamic and physically violent at the particle level. What looks serene and beautiful from a distance is, up close, a storm of colliding ice and rock moving at orbital velocities. Saturn's rings turned out to be one of the most complex structures in the solar system, and the moons orbiting within and around them added more surprises. Voyager discovered several small moons embedded in the ring system itself, their gravitational influence sculpting gaps and waves in the surrounding material. The moon Mimas, barely 400 miles across, was responsible for the largest gap in Saturn's rings, the Cassini division, through a gravitational resonance that clears particles from that region as reliably as a broom sweeping a path. Enceladus, another small icy moon, showed hints of a surface that was puzzlingly young and smooth, a mystery that would not be resolved until the Cassini mission arrived decades later and discovered geysers of water ice erupting from its south pole, evidence of yet another subsurface ocean in the outer solar system. The diversity of Saturn's moons was staggering. Some were heavily cratered and ancient, others were smooth and geologically fresh. Hyperion tumbled chaotically through its orbit, its rotation axis flipping unpredictably, making it one of the most irregularly behaving objects ever observed. Iapetus was split in half, one hemisphere brilliant white and the other coal dark, a two-toned world that defied easy explanation. Every moon was different. Every surface told a different story. The Saturnian system was a solar system in miniature, with more variety packed into the space around a single planet than some models had predicted for the entire outer solar system combined. But the planet's most astonishing moon was not visible to Voyager's cameras at all. It was hidden behind an atmosphere thicker than our own. Titan is the second largest moon in the solar system, bigger than the planet Mercury, and when Voyager 1 flew past it in November of 1980, the cameras could not see the surface. A dense, opaque atmosphere of nitrogen and methane haze blocked everything. The moon was wrapped in an orange blanket so thick that its surface remained a complete mystery for more than 2 decades after the flyby. What the instruments could measure was remarkable. The atmospheric pressure at Titan's surface was 45% greater than at sea level on Earth. The atmosphere was composed primarily of nitrogen, the same gas that makes up most of our own atmosphere, but laced with methane and a cocktail of organic hydrocarbons that gave it the characteristic orange color. The surface temperature was roughly minus 290 degrees Fahrenheit, cold enough for methane to exist as a liquid rather than a gas. The implication was staggering. If methane could be liquid at Titan's surface temperature and pressure, then the same weather cycle that moves water through Earth's atmosphere, evaporation, condensation, and precipitation, could operate on Titan using methane instead. Clouds of methane could form in the upper atmosphere. Methane rain could fall to the surface. Rivers of liquid methane could carve channels across frozen ground, pooling into lakes and seas in low-lying basins. An alien weather cycle, running on fuel instead of water, on a moon orbiting a planet 1 billion miles from the nearest warmth. Voyager could not confirm any of this directly. The cameras were blind behind the orange haze. But the data was suggestive enough to inspire an entire generation of planetary scientists, and eventually the Cassini-Huygens mission, which arrived at Saturn in 2004. The Huygens probe descended through Titan's atmosphere and landed on the surface, confirming everything Voyager had hinted at. Liquid methane lakes, methane rain, river channels cut into ice, a landscape shaped by the same processes that sculpt Earth's terrain, just rebuilt with different chemistry. Voyager 1's close approach to Titan came at a cost. The flyby trajectory pulled the spacecraft above the plane of the solar system, sending it on a path that could never reach Uranus or Neptune. The decision to prioritize Titan meant that Voyager 1's planetary mission was over after Saturn. Everything that followed at the ice giants would fall on its twin alone. Voyager 2 was now the only spacecraft that would ever visit the two most distant major planets, and the worlds waiting for it at the far edge of the solar system were stranger than anything either spacecraft had encountered so far. After Saturn, the twin Voyagers split paths forever. Voyager 1 climbed above the plane of the solar system, pulled upward by its close pass at Titan, on a trajectory that would carry it out of the solar system entirely. It would never visit another planet. Voyager 2 flew onward alone, carrying the full weight of humanity's only chance to study the ice giants up close. Uranus and Neptune sit so far from the inner solar system that they receive a fraction of a percent of the warmth that Earth does. They orbit in perpetual twilight, cold and slow, completing their circuits over decades. Uranus takes 84 years to orbit once. Neptune takes 165. These worlds were discovered with telescopes, studied from afar, and largely ignored by mission planners until the Voyager program made visiting them possible through the chain of gravitational slingshots. Nobody else has ever gone back. No probe has been designed, funded, and launched to revisit either planet in the decades since Voyager 2 flew past. The Cassini mission studied Saturn for 13 years. The Galileo spacecraft orbited Jupiter for 8. Mars has hosted a fleet of rovers, orbiters, and landers spanning 4 decades. Uranus and Neptune have received exactly 1 visit each, lasting a few hours apiece, and no return mission is currently scheduled. Every photograph of Uranus up close was taken during a single pass in January of 1986. Every measurement of Neptune's atmosphere came from a single flyby in August of 1989. Every known characteristic of their magnetic fields, their ring systems, their complex moon families, all of it traces back to a pair of encounters that each lasted less than a day. If Voyager 2 had failed at Jupiter, if its scan platform had jammed permanently at Saturn, if any of 1,000 things had gone wrong in the 13 years between launch and Neptune, we would know almost nothing about 2 entire planets in our own solar system. The data from those flybys is irreplaceable. There are no second chances in the outer solar system. The ice giants matter for a reason that extends far beyond our own solar system. Surveys of exoplanets around other stars have revealed that worlds roughly the size of Uranus and Neptune are among the most common types of planets in the galaxy. They appear far more frequently than gas giants like Jupiter and Saturn, and far more frequently than small rocky worlds like Earth. Understanding what makes these planets tick, how their atmospheres behave, what drives their magnetic fields, how their moon systems form and evolve, is essential for interpreting the data that pours in from exoplanet surveys every year. Yet the only close-up data we have comes from 2 flybys conducted by a spacecraft launched before the space shuttle's first flight. The ice giants are the most common planets in the universe, and we know almost nothing about them. When Voyager 2 reached Uranus in January of 1986, it found a world that defied every assumption scientists had carried into the encounter. The planet lies on its side, tilted 97.8 degrees from its orbital plane. Every other planet in the solar system rotates more or less upright, their poles pointing roughly perpendicular to the direction of travel. Uranus rolls along its orbit like a ball on a bowling lane, with its poles alternately facing toward and away from the distant star over the course of its 84-year orbit. The leading theory is that a massive collision early in the planet's history, possibly with an Earth-sized object, knocked Uranus onto its side. But nobody has proven this, and the details of such a collision raise as many questions as they answer. How does a planet survive an impact large enough to change its axial tilt by 90 degrees? What happened to the debris? How did the moons end up orbiting in the same tilted plane? The magnetic field was equally bizarre. On most planets, the magnetic axis roughly aligns with the rotation axis, pointing in approximately the same direction as the poles. On Uranus, the two are separated by 60 degrees, and the magnetic center is offset from the planet's geometric center by a third of the planet's radius. The field does not extend symmetrically outward from the planet. Instead, it lurches around as Uranus rotates, sweeping through space like a searchlight. 10 new moons appeared in the data, bodies too small and too faint to have been detected from Earth. Winds screamed around the planet at 560 miles per hour. The heat output was 3 times greater than models had predicted, suggesting an internal energy source that remains unexplained. Everything about Uranus contradicted the textbook version of how planets should behave. The tilt was wrong. The magnetic field was wrong. The temperature was wrong. The number of moons was wrong. The ring structure was unlike anything seen at Jupiter or Saturn. Uranus refused to fit into any existing category, and the data raised more questions than it answered. How long has the magnetic field been offset like this? Is the tilt stable, or is the field in the process of reversing? What is the energy source driving winds on a planet that should be thermally dead at this distance from the star? All of this came from a single flyby lasting a handful of hours. No spacecraft has returned since. Everything we know about this world comes from one pass by one machine, and the planetary science community has been requesting a dedicated Uranus orbiter mission for decades. As of today, none has been funded. As Voyager 2 swung behind Uranus, something remarkable happened with the ring system. Viewed from the front, the rings were narrow, dark, and difficult to photograph against the blackness of space. But from behind, with the rings backlit by the faint glow of the distant star, everything changed. Every dust lane, every particle stream that had been invisible from the front suddenly blazed into view. Linda Spilker, who had been with the Voyager mission since she was a graduate student in 1977, called the images spectacular. The backlit view revealed structures that forward-scattered light had completely hidden. Thin sheets of dust, wispy lanes of material orbiting in the spaces between the main rings. All of it suddenly became visible simply because the spacecraft had moved to the other side. The discovery carried a lesson that extended far beyond ring science. The universe looks fundamentally different depending on where you stand. The same structure can appear empty from one angle and full from another. Information hides in the direction of observation, and the only way to find it is to move to a position that nobody has occupied before. Voyager 2, by flying behind Uranus, occupied exactly that position, and the rings rewarded it with secrets they had never shown to any telescope on Earth. Uranus had been full of surprises. A sideways planet with an offset magnetic field, unknown moons appearing in every frame, winds that should not have existed given the planet's distance from any significant heat source, and a ring system that concealed its true complexity until someone looked at it from the wrong direction. The encounter lasted less than a day. When Voyager 2 pulled away and aimed for its next target, it left behind a planet that science understood only slightly better than before it arrived. The ice giants remain, to this day, among the least studied major objects in the solar system. 3.5 years of travel separated Uranus from Neptune. During that long coast, the spacecraft crossed more than 1 billion additional miles of empty space. The instruments ran in a low-power configuration, collecting baseline measure capture usable images. Longer exposures meant the spacecraft's motion would blur the photographs unless compensated for. Engineers developed a technique called image motion compensation, rotating the entire spacecraft slowly during each exposure to track the target, essentially panning the camera like a photographer following a moving subject. The technique had never been attempted at this level of precision. It worked. Communication delays had grown to over 4 hours each way, making real-time course corrections impossible. Every maneuver had to be pre-programmed, uploaded to the spacecraft's computer, and executed autonomously. If something went wrong during closest approach, the engineers on Earth would not learn about it for more than 4 hours, and their corrective commands would take another 4 hours to arrive. The Neptune encounter was, in every practical sense, a robotic operation conducted without human supervision at the decisive moment. The preparation paid off. The image motion compensation technique produced photographs of stunning clarity, capturing details on Neptune and its moons that ground-based telescopes could never resolve. The communication protocols, tested and refined over 12 years of increasingly distant operations, held firm despite the 4-hour signal delay. Every programmed maneuver executed correctly. The spacecraft performed the most complex autonomous sequence of its entire mission without a single intervention from Earth. When the data began arriving back at the Jet Propulsion Laboratory, the quality exceeded expectations. When Voyager 2 arrived, Neptune did not disappoint. It terrified. Voyager 2 reached Neptune on August 25, 1989, after traveling for 12 years and more than 4 billion miles from Earth. The encounter was the final planetary flyby in the Voyager program. The engineering team knew they would never get another chance at an ice giant. They squeezed every possible measurement from the spacecraft's instruments during the brief window of close approach. The first major discovery was a storm. A massive dark oval, quickly named the Great Dark Spot, sat in Neptune's southern hemisphere, rotating counterclockwise against bands of white methane clouds. The storm was roughly the size of Earth. On a planet this far from the nearest star, where the energy input from sunlight is vanishingly small, a storm of that magnitude should not have been possible. Nobody could explain where the energy came from. And then the wind measurements arrived. 1,500 miles per hour, the fastest winds ever recorded anywhere in the solar system. For comparison, the strongest hurricanes on Earth produce sustained winds of roughly 200 miles per hour. Neptune's winds were nearly 8 times faster, howling around the planet with enough force to strip material from the cloud tops and fling it into the upper atmosphere. The explanation, as far as scientists could determine, lay inside the planet itself. Neptune radiates 2.5 times more energy than it receives from the distant star. Something in its interior, possibly the decay of radioactive elements deep within the core, or the slow contraction of the planet itself, is generating heat that drives atmospheric circulation far beyond what external energy alone could produce. The planet runs on its own internal engine. Neptune has no solid surface in any conventional sense. No ground to stand on, no bedrock to drill into, no mountains to block the wind. The atmosphere extends downward continuously, becoming progressively denser and hotter with depth. There is no clear boundary between gas and liquid. The transition is gradual, a slow compression that takes hydrogen, helium, methane, and ammonia, and squeezes them through states of matter that do not exist naturally anywhere on Earth. At extreme depths, the temperature and pressure may be high enough to compress carbon into diamonds that rain slowly toward the core. Above this, the winds encounter nothing but more atmosphere in every direction. There are no obstacles to slow them, no surface friction, no terrain to break the flow. The result is the most violent atmospheric system in the known solar system, wrapped around a planet that barely receives enough light from its star to cast a shadow. Neptune's largest moon turned out to be one of the most astonishing objects Voyager encountered during the entire mission. Triton is one of the coldest places ever measured in the solar system. The surface temperature hovers at 37 Kelvin, roughly minus 391 degrees Fahrenheit. At that temperature, nitrogen itself freezes solid. The entire moon is coated in a thin shell of nitrogen ice, with patches of frozen methane and carbon monoxide creating a pinkish tint near the southern polar regions. Voyager 2 flew past Triton during its Neptune encounter, and the images that came back were unlike anything the mission had produced at any previous stop. The surface was young, geologically speaking, with very few impact craters. Dark streaks ran across the southern polar cap, fan-shaped deposits that looked like stains on the ice, each one pointing in the same direction as if drawn by a prevailing wind. Then the team found the geysers. Active eruptions were punching through the frozen surface, launching columns of dust-laden nitrogen gas 5 miles into the thin atmosphere. For scale, the famous Old Faithful geyser at Yellowstone National Park reaches a maximum height of roughly 200 feet. Triton's geysers were 25 times taller, blasting frozen material from a surface so cold that the nitrogen forming the plume had been a solid block of ice moments before eruption. The energy source is believed to be the feeble warmth of distant starlight, which seems paradoxical on a world where the temperature never rises above minus 300 degrees. But the process is subtle and elegant. Even at Neptune's enormous distance, a trickle of light energy can penetrate the transparent nitrogen ice and reach dark particles of dust or organic material trapped beneath the surface. These dark particles absorb the energy more efficiently than the clear ice around them, warming the trapped gas. The heated gas builds pressure beneath the ice until it fractures the cap above and jets outward in an explosive release. The dark streaks on the surface are the fallout deposits from these eruptions, particles carried downwind by Triton's thin atmosphere and draped across the frozen landscape like ash from a volcano. Triton is one of only 3 objects in the solar system known to have an atmosphere composed primarily of nitrogen. The other 2 are Earth and Titan. The coincidence is striking. Nitrogen atmospheres appear on a warm, wet world teeming with life, on a moon drenched in hydrocarbon rain, and on a frozen rock near absolute zero at the outermost edge of the planetary system. The chemistry that produces these atmospheres is different in each case, yet the result is eerily similar. This cold, distant moon, orbiting a planet that receives almost no meaningful energy from the distant star, has an atmosphere, weather, and active geology driven by processes so subtle that scientists are still debating exactly how they work. The processes that drive these phenomena are subtle, fragile, and utterly unlike anything on Earth, yet they produce landscapes of startling beauty and violence. Linda Spilker had been with Voyager since 1977. By the time the spacecraft reached Neptune, she had spent 12 years watching data arrive from the outer solar system. During the closest approach phase, the data came in on small television monitors at the Jet Propulsion Laboratory, building up line by line, each row of pixels revealing surfaces and features that no human eye had ever seen. She put a sleeping bag under her desk. The images arrived at all hours, and she refused to miss any of them. Triton's surface materialized on her screen in real time: pink nitrogen ice, dark geyser fallout streaks, a landscape sculpted by forces operating at temperatures that would freeze the air out of a room in seconds. "I remember watching those first pictures come back," she said later. "It was just so exciting to know I am seeing data from this world that we really do not know much about." The Neptune encounter was the emotional peak of the planetary mission. 12 years of travel, 4 giant planets, more discoveries than any single mission in the history of space exploration. Volcanic moons spewing material into space at a rate of 1 ton per second. A possible ocean beneath kilometers of ice that might harbor life. Storms with winds 8 times faster than the worst hurricanes on Earth, powered by internal heat on a planet that receives almost no energy from its star. Rings around every giant planet, each system more complex than the last. Geysers erupting 5 miles high from surfaces so cold that nitrogen freezes solid, an atmosphere thicker than our own wrapped around a moon smaller than Mercury, and dozens of previously unknown moons, each one a world unto itself, catalogued during flybys that lasted hours and will not be repeated in our lifetimes. Then it was over. Voyager 2 flew past Neptune and kept going, heading outward into the emptiness beyond the last major planet. The images stopped arriving. The cameras would soon be shut down permanently. The next phase of the mission would have no pictures, no dramatic visual reveals, no surfaces to map. The Voyagers were entering a region where the only data that mattered was invisible: magnetic fields, charged particles, plasma oscillations. The age of images was ending, and the age of silence was beginning. But before the cameras went dark for good, Carl Sagan had one last request. He had been making it for 7 years, and this time, NASA was finally going to listen. Ed Stone had been the Voyager project scientist since 1972, 5 years before the spacecraft even launched. He would remain in that role for over 50 years, shepherding the mission through every planetary encounter, every instrument failure, every budget fight, and every moment of discovery. When Triton's geysers appeared on the screen, Stone was there. When the heliopause was finally confirmed, Stone was there. His career and the mission were inseparable. Stone understood something about Voyager that most people missed. The mission was not just about the data. It was about what happens to a species when it sees its own neighborhood for the first time. Every image, every temperature reading, every magnetic field measurement changed the way scientists thought about the solar system, and through them, the way everyone else thought about their place in it. Stone once described the feeling of the planetary encounters as a gift, each flyby, delivering information so unexpected and so beautiful that the scientists receiving it felt like they were opening something precious. When the cameras powered off, Stone was there to authorize the sequence. When the engineers debated whether to risk disabling the voltage regulator, Stone supported the decision. He would remain at his post until his death in 2024, at the age of 88. He had overseen the longest, farthest voyage of exploration in human history, from the launch pad at Cape Canaveral to the shores of interstellar space, a span of 47 years and counting, and he did it with a quiet enthusiasm and dedication that never diminished across 5 decades of discoveries, setbacks, near failures, and triumphs. The mission outlived many of the people who built it. The spacecraft are still going, the data is still arriving, and somewhere in the Jet Propulsion Laboratory, a new generation of engineers maintains the connection to machines that were designed before they were born, using protocols developed by colleagues they never met, keeping alive a mission that was supposed to last 4 years. For 7 years, the answer was no. Carl Sagan had proposed the idea in 1981, shortly after Voyager 1 completed its Saturn flyby and climbed above the plane of the solar system. The concept was disarmingly simple. Before the cameras were shut down forever, turn Voyager 1 around and take a photograph of Earth from the edge of the solar system. A portrait of our planet from a distance so great that the image would show essentially nothing. A dot, maybe less than a dot. NASA officials at the Jet Propulsion Laboratory rejected the proposal on practical grounds. There was no scientific value in photographing a planet that would occupy less than a single pixel. The cameras would need to be powered up and carefully aimed, consuming time and resources that were better spent on other observations. There was also a risk that pointing the cameras so close to the nearby star could damage the optics. The project leaders were not willing to take that chance. Sagan proposed it again, and again, and again over 7 years. His argument was never about science. He wanted humanity to see itself from the outside. The Apollo missions had produced the famous Earthrise photograph, an image of our planet as seen from lunar orbit that had changed the way an entire generation thought about their home. Sagan believed that a photograph taken from 100 times farther away could do something even more powerful. It could show a species that had spent its entire existence on a single world what that world actually looks like from the perspective of the cosmos. A speck, a grain, a mote of dust in an ocean of emptiness. Allies within the Voyager team gradually came around to Sagan's vision. The technical support materialized. The political obstacles were navigated. The observation was scheduled, and on February 13th, 1990, Voyager 1 warmed its cameras for 3 hours and prepared to look back over its shoulder for the first and last time. The spacecraft was nearly 4 billion miles from Earth when it began shooting. The science platform swiveled to aim the cameras at Neptune first, then Uranus, then Saturn, Mars, Jupiter, and finally, Earth and Venus. 60 frames in total, composing a mosaic that would become known as the family portrait of the solar system. The first view of our planetary neighborhood taken from the outside. Earth appeared in a single narrow-angle frame, a faint point of light less than 1 pixel wide, caught in a band of scattered light from the nearby star. The image was captured at 4:48 Greenwich Mean Time on February 14th, 1990, Valentine's Day. 34 minutes after the shutter closed on that final frame, the cameras were powered down permanently. They would never be turned on again. It took weeks for all the image data to arrive. The signal traveled at the speed of light across nearly 4 billion miles of empty space, and the bandwidth was achingly slow. The final download required 4 separate communication sessions with the Deep Space Network and was not completed until May 1st, 1990. Candice Hansen-Koharchek, one of the scientists who had developed the command sequence controlling each photograph's timing and exposure, was sitting in front of a computer at the Jet Propulsion Laboratory with her shades drawn when she noticed the dot, a speck, suspended in a diagonal ray of scattered light, barely distinguishable from the noise in the image. "It was just a little dot," she said, "about 2 pixels big, 3 pixels big, so not very large. I still get chills down my back because here was our planet, bathed in this ray of light, and it just looked incredibly special." Sagan saw the image and wrote the words that would define it for every generation that followed. "Look again at that dot. That is here. That is home. That is us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. The pale blue dot remains the most distant photograph of Earth ever taken. Voyager 1 was 4 times closer to our planet at that moment than it is today. The image has never been repeated. No spacecraft currently in operation is positioned to take a comparable photograph, and none is planned. The pale blue dot stands alone, a single frame captured during the last 34 minutes of a camera's life, showing a world that appears so small and so vulnerable that every border drawn on its surface, every war fought over its territory, every argument about its resources becomes, from that vantage point, absurd. Sagan's words entered the culture and stayed there. They are quoted in classrooms, printed on posters, engraved on plaques. The image has been reproduced millions of times, and yet its power comes from a paradox. The photograph shows almost nothing. The planet is barely visible. The image is mostly empty space, with a single, nearly invisible speck. That is the point. The less you see, the more you understand. With the cameras off, both Voyagers became blind. The instruments that remained active measured forces that could not be seen or photographed. The strength and direction of magnetic fields, the density and speed of charged particles, the frequency of plasma oscillations rippling through the medium around them. The spacecraft could no longer watch. They could only listen and feel. This transition happened in 1990, and it fundamentally changed the character of the mission. The planetary phase had been visual, dramatic, and immediate. Images appeared on screens within hours of being taken, and the world shared in the excitement of discovery as it happened. The interstellar phase was invisible, gradual, and measured in years. Changes in the environment unfolded over distances so enormous that a trend might take an entire decade to confirm. The drama shifted from photographs to numbers, from surfaces to fields, from the spectacular to the subtle. Both spacecraft continued outward at their cruising speeds. Voyager, one at roughly 38,000 miles per hour, Voyager 2 at about 35,000. The instruments recorded a slow, steady decline in the strength of the solar wind, the stream of charged particles blowing outward from the star. Cosmic rays from beyond the solar system, particles accelerated by distant supernovae and other violent galactic events, gradually intensified year by year. The boundary between the star's domain and interstellar space was somewhere ahead, but nobody knew exactly where. Models predicted that the heliopause, the point where the outward pressure of the solar wind equals the inward pressure of the interstellar medium, should lie somewhere between 80 and 150 astronomical units from the star. 1 astronomical unit is the distance from Earth to the star at the center of our system, about 93 million miles. The uncertainty in the models spanned a range of more than 6 billion miles. The only way to find the boundary was to fly through it and see what the instruments recorded. Both Voyagers drifted forward, year after year, sending back numbers that shifted by tiny increments. The waiting lasted more than 2 decades. Voyager 1's cameras had been off for 22 years before the first clear signs of the boundary appeared. The termination shock hit first. This is the region where the supersonic solar wind, blasting outward at hundreds of miles per second, abruptly drops below the speed of sound as it encounters the resistance of interstellar gas pushing inward. Think of it as the point where a river's current runs into the ocean and suddenly decelerates, churning into turbulence. Voyager 1 crossed this boundary in December of 2004, at a distance of 94 astronomical units from the star. Voyager 2 followed in 2007, crossing at 84 astronomical units, roughly a billion miles closer. The difference in crossing distances revealed something important. The heliosphere, the protective bubble of solar wind surrounding our star system, is not a perfect sphere. It is asymmetric, compressed on one side by the interstellar magnetic field and stretched on the other. The boundary moves, pushed inward and outward by changes in solar activity in the roughly 11-year solar cycle. The Voyagers crossed it at different points, under different conditions, at different distances, giving scientists their first evidence that the shape of the bubble is lumpy and dynamic rather than smooth and stable. Beyond the termination shock lies the heliosheath, a broad, turbulent region where the slowed solar wind piles up and grows denser as it presses against the interstellar medium ahead. Both Voyagers spent years crawling through this zone, and the data they returned showed conditions that no model had accurately predicted. The plasma was hotter than expected in some areas. The flow patterns were erratic, moving in directions that defied the theoretical calculations. The magnetic field fluctuated in ways that suggested the heliosheath was far more chaotic than anyone had imagined. Voyager 1 entered a zone within the heliosheath, where the radial flow of the solar wind dropped to nearly zero. Scientists called it the stagnation region. The plasma appeared to have simply stopped moving outward, as if it had hit an invisible barrier. Engineers on Earth commanded the spacecraft to roll 90 degrees and hold that attitude for several hours, measuring in a different direction to determine whether the flow had been diverted sideways rather than disappearing. The result was no. The flow had ceased. The wind that had been blowing outward from the star for billions of years had run out of momentum. Ahead lay the heliopause itself, the final boundary between the stellar bubble and the galaxy beyond. And the crossing, when it came, would be unlike anything the theorists had predicted. August 25th, 2012, 121.6 astronomical units from the star, roughly 11.3 billion miles from Earth. On that date, Voyager 1's cosmic ray instrument recorded a sudden surge in the intensity of galactic cosmic rays, high-energy particles that originate from supernova explosions and other violent events beyond the solar system. Simultaneously, the abundance of lower-energy particles that originate from within the heliosphere dropped to undetectable levels. Solar particles vanished. Galactic particles flooded in. The spacecraft had punched through the heliopause and entered interstellar space. It was the first time a human-made object had crossed that boundary. The first time any instrument had directly sampled the medium that fills the space between the stars. The moment should have been an immediate historic announcement, a milestone confirmed and celebrated in real time. Instead, the Voyager science team hesitated. For 13 months, NASA said nothing publicly. The silence was deliberate. The problem was the magnetic field. Every theoretical model predicted that crossing the heliopause would produce a sharp change in the direction of the magnetic field. Inside the heliosphere, the field is shaped by the star's rotation, creating a spiral pattern that extends outward. Outside, it should align with the galactic magnetic field, which points in a completely different direction. Voyager 1's magnetometer showed an increase in field strength at the crossing point, but the direction barely changed. The field on the other side looked almost the same as the field inside the bubble. Stamatios Krimiges, one of the principal investigators on the mission, later said that nature has not read the theorists' papers and did not know it was supposed to change the magnetic field direction. The quip captured the scientific community's frustration, the most important boundary crossing in the history of space exploration, and nature refused to behave the way the textbooks predicted. The result was confusing enough that some scientists argued Voyager had not actually crossed the boundary at all. Perhaps it was in some intermediate zone, a region still partially connected to the heliosphere. The debate was intense and unresolved for months. The spacecraft's plasma instrument, the one device that could have settled the question definitively by measuring the density of the surrounding medium, had been broken since 1980. It failed during the Saturn flyby 32 years earlier, and there was no way to fix it from 15 billion miles away, into the interstellar plasma surrounding the spacecraft and set the medium vibrating. Electrons in the plasma began oscillating at frequencies directly related to the density of the surrounding gas, and those oscillations generated radio waves that Voyager's plasma wave instrument could detect. The instrument had recorded nothing for 7 years. Suddenly, it lit up. The frequency of the oscillations told scientists everything they needed to know. The electron density at Voyager's location was approximately 40 to 50 times greater than the density inside the heliosheath. This was cold, dense, interstellar plasma, exactly what should exist beyond the heliopause. The interstellar medium had rung like a bell, struck by a pressure wave that originated at the star and traveled billions of miles to reach the spacecraft. A re-examination of older data revealed a fainter set of oscillations from October and November of 2012, likely produced by earlier solar activity. Extrapolating backward, the onset of those oscillations coincided precisely with the August 25th date, when the cosmic ray levels had shifted dramatically. The evidence was now overwhelming. On September 12th, 2013, more than a year after the crossing occurred, NASA announced that Voyager 1 had entered interstellar space. The spacecraft had become the first human-made object to reach the medium between the stars, the signal confirming it had traveled for over 16 hours at the speed of light to reach Earth. And then the analysis had taken another 13 months of human deliberation to resolve. The galactic environment that Voyager entered was supposed to be quiet, uniform, and calm, a serene backdrop against which the heliosphere floated. That expectation was wrong almost immediately. and what the spacecraft found on the other side would force scientists to rethink their models of the space between the stars. In 2021, a doctoral student at Cornell University named Stella Koch-Ocker was examining data transmitted by Voyager 1 from beyond the heliopause. Between the occasional bursts of plasma oscillation triggered by solar storms, she found something hiding in the background noise, a constant, faint, monotone signal at a narrow frequency, a hum emanating from the interstellar gas itself. The plasma wave instrument had been recording it the entire time, but the signal was so subtle that it required careful filtering to extract from the surrounding noise. When Ocker isolated it, the result was unmistakable, a persistent drone, steady and unchanging, produced by the natural oscillation of electrons in the interstellar medium. It is very faint and monotone, because it is in a narrow frequency bandwidth, Ocker explained. We are detecting the faint, persistent hum of interstellar gas. James Cordes, the senior author on the study, described the sound with an image that captures its character perfectly. The interstellar medium is like a quiet or gentle rain. In the case of a solar outburst, it is like detecting a lightning burst in a thunderstorm, and then it is back to a gentle rain. The discovery means that interstellar space has a voice. The void between the stars produces a quiet, constant tone at a frequency corresponding to about 1 electron per cubic inch, a density so thin that a room-sized volume of this space would contain fewer particles than you can count on one hand. Yet those particles vibrate, and Voyager was the first machine sensitive enough to hear them. To understand how thin this is, consider that the air you are breathing right now contains roughly 25 billion molecules per cubic inch. Interstellar space contains 1 electron in the same volume. The ratio between the density of Earth's atmosphere and the density of interstellar plasma is the ratio between an ocean and a single drop of water stretched across a continent. The space between stars is emptier than the best vacuum any laboratory on Earth has ever produced. And yet this almost nothing vibrates at a frequency that a sufficiently sensitive instrument can detect. The hum is real. The emptiness is singing. The hum also revealed that there is more low-level activity in the interstellar medium than scientists had assumed. The space between stars is not an inert vacuum. It is a tenuous but active environment, shaped by magnetic fields, cosmic rays, and the distant influence of every star in the neighborhood. The gentle, persistent rain of plasma oscillation continues unbroken across the millennia, a baseline sound that has been playing since long before our star system formed and will continue long after it dies. Voyager was listening to the galaxy breathing, and the sound has not stopped since the first detection. 6 years after Voyager 1, its twin followed through the boundary. On November 5th, 2018, Voyager 2 crossed the heliopause at approximately 119 astronomical units from the star, roughly 2.5 astronomical units closer than its sibling had crossed 6 years earlier. The closer crossing distance was significant. It meant the heliosphere is not symmetrical. The interstellar magnetic field pushes harder against the southern hemisphere of the stellar bubble, compressing it inward. Voyager 2 approached from below the ecliptic plane, heading in a different direction than Voyager 1, and the boundary it encountered was measurably closer to the star. 2 crossing points, 6 years apart, in different directions, at different distances. Together, they gave scientists their first 3-dimensional picture of where the heliosphere ends and the galaxy begins. The most valuable thing about Voyager 2's crossing was a piece of hardware that had been broken on Voyager 1. Since 1980, the plasma science instrument, Voyager 1's plasma detector, had failed during the Saturn flyby, which was precisely why the heliopause crossing in 2012 had been so difficult to confirm. Scientists had spent 13 months arguing about whether the boundary had really been crossed, because the one instrument that could settle the question definitively was dead. Voyager 2's identical instrument still worked. For the first time, scientists could directly measure the temperature, density, and speed of interstellar plasma at the exact moment of crossing. The data showed a sharp, dramatic jump in plasma density, confirming that the heliopause is a real, persistent boundary between two fundamentally different environments. On one side, hot, tenuous solar wind plasma. On the other, cold, dense interstellar gas. The transition happened over a distance so short that the spacecraft crossed it in less than a day. Every observation was consistent with Voyager 1's crossing 6 years before. The heliopause was real. It was persistent. And both spacecraft were now on the other side, traveling through the medium that fills the space between the stars. The two crossings, taken together, represent one of the most significant achievements in the history of space exploration. Two machines, launched in 1977, designed for a 4-year mission to Jupiter and Saturn, had survived long enough to reach and cross a boundary that humanity had theorized about for decades but never directly measured. The data from those crossings will inform models of stellar physics, heliospheric dynamics, and interstellar medium chemistry for generations. Every future spacecraft sent beyond the solar system will calibrate its instruments against what the Voyagers measured at the boundary. The baseline was set by 2 probes running on technology that would have been obsolete by the time the personal computer became a household item. Scientists had expected the region beyond the heliopause to be quiet, a uniform expanse of cold interstellar gas, gently permeated by galactic cosmic rays and threaded with magnetic fields pointing in a fixed direction. The kind of environment where measurements would be steady and uneventful, a calm sea after the turbulence of the heliosheath. The reality was more complicated. After entering interstellar space, Voyager 1 was expected to settle into a routine of steady, uneventful measurements. The galactic medium was supposed to be calm, a serene bath of cold gas and gentle magnetic fields with no significant variations on the scale of astronomical units. Instead, the spacecraft continued to detect occasional spikes in cosmic ray intensity. These arrived like tsunamis, sudden increases that built rapidly and then subsided over weeks or months, disrupting the expected baseline and producing data that no existing model could fully explain. The bursts were not random. They correlated with solar activity, storms that had erupted on the face of the star months or years earlier, their effects propagating outward through the heliosphere at finite speed and eventually crashing into the interstellar medium beyond the heliopause. The implication was profound. The stellar influence extends beyond its own bubble. Pressure waves generated by solar storms do not stop at the heliopause. They cross it, and they disturb the interstellar medium on the other side. The boundary is not a wall. It is a membrane, permeable to certain kinds of energy. A region scientists had assumed was isolated from the star turned out to be connected to it, still shaped by its outbursts even at distances exceeding 11 billion miles. In October of 2020, both Voyagers detected an unexpected increase in the density of the interstellar plasma itself. The finding was significant enough to warrant formal publication. According to the researchers, the density gradient was a large-scale feature of the very local interstellar medium, suggesting that as the spacecraft move outward, the space around them is gradually becoming denser, more populated with the raw material of the galaxy. Nobody had predicted this trend. The models assumed uniform density beyond the heliopause, with variations occurring only on scales of light years. The frontier is restless, structured, and connected to the star that launched these machines nearly 50 years ago. The Voyagers are revealing a galactic neighborhood more complex, more active, and more surprising than anyone imagined. And they are doing it with instruments that are running out of power. The unexpected complexity of the interstellar medium has implications that extend far beyond the Voyager mission. If the space between stars is not uniform, if it contains structures, density gradients, and pressure waves on scales that current models do not account for, then the environment through which our entire solar system moves is more textured and more variable than anyone thought. The heliosphere is not floating in a calm bath. It is plowing through a medium that pushes back, that varies in density and direction over distances of just a few astronomical units, that carries the imprint of events, supernova explosions, stellar winds, collisions between gas clouds that occurred millions of years ago and thousands of light years away. The Voyagers are sampling this medium in real time at 2 different locations, with instruments that were not designed for the task, but are performing it anyway. Every measurement they send back adds a data point to a map that no other instrument can provide. When they go silent, that map will freeze in place, and the next direct measurement of interstellar space will not be taken until another spacecraft follows the same path, decades or centuries from now. Each Voyager carries 3 radioisotope thermoelectric generators, devices that convert the heat of decaying plutonium-238 into electrical current. The plutonium was loaded in 1977, and it has been decaying steadily ever since. Each year, the generators produce approximately 4 fewer watts of electricity than the year before. The decline is slow, predictable, and completely irreversible. Nothing can stop it. Nothing can replace the fuel. The power will continue dropping until the generators can no longer sustain any instrument aboard either spacecraft. At launch, each Voyager's generators produced roughly 470 watts. Today, each spacecraft generates around 249 watts. A standard kitchen toaster uses 800 to 1500 watts. The total electrical budget for humanity's farthest traveling exploration mission is less than the power drawn by the smallest appliance in most homes. The instruments have been shutting down for decades. During the planetary encounters, all 10 science instruments on each spacecraft were running simultaneously, drawing power for cameras, spectrometers, photopolarimeters, and charged particle detectors. As the planetary mission ended and instruments became redundant for the interstellar phase, the engineering team powered them off one by one. The cameras went first. In 1990, the ultraviolet spectrometer followed. Other instruments were shut down over the years as priorities shifted and power margins tightened. By February of 2025, the shutdowns reached the core science instruments that had been measuring the interstellar environment. On February 25th, NASA powered off Voyager 1's cosmic ray subsystem, the very instrument that had played a central role in detecting the heliopause crossing 13 years earlier. 1 month later, on March 24th, Voyager 2's low-energy charged particle instrument went dark. 3 science instruments remain active on each spacecraft. On Voyager 1, the magnetometer, the plasma wave subsystem, and the low-energy charged particle instrument, which is scheduled to be shut off in 2026. On Voyager 2, the magnetometer, the plasma wave subsystem, and the cosmic ray subsystem, also slated for shutdown in 2026. After that, both spacecraft will be operating with only 2 instruments each, the minimum toolkit for studying the space between the stars. Every other measurement capability that the mission once possessed, the cosmic ray counts, the charged particle analysis, the plasma density readings, all of it will be gone. The remaining instruments will tell scientists how strong the magnetic field is and how many electrons are nearby. That is all. Everything else about the interstellar medium, its temperature, its composition, its flow direction, its interaction with the stellar wind far behind, will have to be inferred from models built on the data collected before the instruments went dark. Suzanne Dodd, the Voyager project manager at the Jet Propulsion Laboratory, delivered the numbers without softening them. If we do not turn off an instrument on each Voyager now, she said in early 2025, they would probably have only a few more months of power before we would need to declare end of mission. The engineering team had been stretching the power budget for years, finding increasingly creative ways to squeeze extra months from a diminishing supply. In 2023, they made a calculated gamble on Voyager 2. They disabled the voltage regulator safety circuit, a protection system designed to shield the instruments from electrical surges, and redirected that small amount of reserved power directly to the science instruments. The risk was real. Without the voltage regulator, a power surge could damage or destroy the remaining equipment. But the Voyager spacecraft had been running on remarkably stable power for decades, and the engineering team judged the probability of a catastrophic surge to be low enough to justify the trade. The gamble bought an estimated 3 extra years of science from a power budget that had been running on fumes. Variable voltages pose a small risk, Suzanne Dodd acknowledged, and the alternative offers a big reward of being able to keep the science instruments turned on longer. Linda Spilker, Voyager's project scientist, who had put a sleeping bag under her desk during the Neptune encounter 36 years earlier, framed the situation with the weight of everything the mission had achieved. Every minute of every day, the Voyagers explore a region where no spacecraft has gone before. That also means every day could be our last. But that day could also bring another interstellar revelation. So, we are pulling out all the stops, doing what we can to make sure Voyagers 1 and 2 continue their trailblazing for the maximum time possible. The team is buying time with ingenuity and acceptable risk. Every optimization, every creative workaround, every calculated gamble adds months or years to a mission that was supposed to last 4. The engineers who maintain the Voyagers today were children when the spacecraft launched. They inherited a machine they did not build, running software they did not write, powered by fuel they cannot replenish. Their job is to keep it alive as long as possible, knowing that the fundamental constraint is physics. Plutonium decays according to its half-life, and no amount of clever engineering can slow down nuclear physics. Power drops, instruments go dark, and nobody can send more fuel to a spacecraft 15 billion miles away, traveling at 38,000 miles per hour in the opposite direction from Earth. The only direction for the power curve is down, and the only question is how much science can be extracted before the curve reaches zero. Each Voyager launched with 10 science instruments. The cameras were the first to go, powered down in 1990 after the pale blue dot image and the end of the planetary mission. The photopolarimeter and the ultraviolet spectrometer followed over the years. The plasma science instrument on Voyager 1 had already failed on its own during the Saturn flyby in 1980, a malfunction that would complicate the interpretation of data for decades. One by one, the instruments that had revealed the outer solar system in unprecedented detail were switched off to conserve the dwindling electrical supply. Each shutdown was a loss, a window closing on a type of measurement that could never be recovered, the cosmic ray subsystem that detected the heliopause crossing, the charged particle detectors that measured the solar wind's dying gasp. Every instrument contributed something unique to our understanding of the space between the stars, and every shutdown removed a capability that no other spacecraft could replace. By 2026, both spacecraft will operate with only 2 instruments each, the magnetometer and the plasma wave subsystem. The magnetometer measures the strength and direction of the local magnetic field. The plasma wave subsystem measures the density of electrons in the surrounding medium. Together, they provide the minimum information needed to characterize the interstellar environment. How strong is the field, and how dense is the plasma? Engineers estimate that the radioisotope generators will be unable to power any science instrument by approximately 2030. The generators may still produce enough electricity after that point to run the spacecraft's basic engineering systems. The heaters that prevent fuel lines from freezing, the attitude control system that keeps the antenna pointed toward Earth, and the transmitter that broadcasts the signal homeward. The transmitter operates at 23 watts. As the spacecraft move further from Earth, the signal grows weaker with the square of the distance. The Deep Space Network's 70-meter dishes can currently detect it, but there is a distance beyond which even those enormous antennas cannot distinguish the Voyager signal from the background noise of the cosmos. That threshold will be crossed sometime around 2036. After that, the signal will still be there, propagating outward at the speed of light, growing fainter with every passing mile. But no receiver on Earth will be able to hear it. The communication link between Earth and the Voyagers is one of the most remarkable engineering achievements in human history, and it deserves a moment of attention before it disappears. The spacecraft's transmitter broadcasts at 23 watts, roughly the power of a small lamp. From a distance of 15 billion miles, the signal that reaches Earth has been diluted by the inverse square law to a power level measured in billionths of a billionth of a watt. The Deep Space Network's 70-meter dishes, the largest steerable radio antennas on Earth, are the only instruments capable of detecting it. Each communication session involves aiming one of these massive dishes at a point in the sky where the spacecraft was more than 23 hours ago, because the signal takes that long to arrive. The dish collects the signal for hours at a time, and sophisticated receivers cooled to near absolute zero amplify it above the background noise. The data arrives at speeds that would have been considered slow in the era of dial-up internet, around 160 bits per second from Voyager 1. At that rate, a single high-resolution photograph would take weeks to download. The engineering data that still arrives from the spacecraft fits comfortably in a text message, yet each packet contains measurements from the most distant laboratory in human history. The people who maintain this link work in shifts around the clock, coordinating antenna time across 3 Deep Space Network sites in California, Spain, and Australia. Voyager 2 can only be contacted from Canberra because its southern trajectory has carried it below the horizon of the Northern Hemisphere stations. If the Canberra dish goes offline for maintenance, Voyager 2 goes silent until it comes back. The entire communication chain depends on aging ground infrastructure, institutional knowledge held by a shrinking team of specialists, and a transmitter in interstellar space that has been running continuously for nearly half a century without a single repair. The end will arrive quietly. There will be no dramatic final transmission, no carefully composed farewell message beamed across the void. The data stream will simply become too faint to distinguish from noise. The engineering team will attempt to boost the signal, adjust the receiving parameters, fine-tune the antenna tracking, and try again. At some point, the numbers on their screens will dissolve into static, and the controllers at the Jet Propulsion Laboratory will acknowledge that the connection has been lost. The last round-trip communication with Voyager 1 already takes nearly 48 hours. A command sent from Earth travels over 15 billion miles, arrives at the spacecraft more than 23 hours later, is processed by the onboard computer, and the response begins its own 23-hour journey back. A conversation that takes almost 2 full days to complete. By the time the end comes, that delay will be even longer, and each exchange will carry increasing uncertainty about whether the signal received is genuine data or just patterns in the noise. After the signal dies, both Voyagers will continue moving at their current velocities. Voyager 1 at approximately 38,000 miles per hour, Voyager 2 at roughly 35,000. They will not slow down. There is nothing in interstellar space to create meaningful friction or resistance. No atmosphere, no drag, no countervailing force of any kind. The spacecraft will coast on their current trajectories forever, blind and mute, for a period of time that makes the entire history of human civilization look like a brief flash. The instruments will be frozen in their final positions. The golden records will sit in their aluminum jackets, undisturbed. The antenna will continue pointing toward a planet that will forget the spacecraft long before the spacecraft forget their heading. 2 small machines, each the size of a compact car, drifting through the emptiness between the stars at a speed that would cross the continental United States in roughly 5 minutes, heading nowhere in particular. With no one listening, the antennas will still be pointed at Earth, aimed at a planet whose inhabitants have long since moved on to other projects, other crises, other explorations. The spacecraft will maintain their heading with the precision of their frozen attitude control systems, aimed at a world that launched them nearly 50 years earlier, and then, at some point in the 2030s, lost the ability to hear their reply. In approximately 40,000 years, Voyager 1 will drift within 1.6 light-years of a red dwarf star called Gliese 445, located in the constellation Camelopardalis. Gliese 445 is currently moving toward our solar system, and by the time Voyager arrives in its general neighborhood, the star will be one of the closest to where we live now. 1.6 light-years is roughly 9.3 trillion miles. At that distance, the star would appear as a noticeably, which by that point will be the closest star to our own system. The passage distance will be a few light-years, close enough to be notable on a star chart, meaningless in terms of physical proximity. Then, in approximately 296,000 years, Voyager 2 will pass 4.3 light-years from Sirius, the brightest star visible from Earth. Still not close, still just drifting through. These are the closest stellar encounters either spacecraft will make in the foreseeable future, and none of them constitute an arrival. The emptiness between stars is so vast that even after traveling for tens of thousands of years at speeds that would cross the continental United States in 5 minutes, the Voyagers will still be isolated. They will pass through the periphery of stellar neighborhoods, never entering, never stopping, never slowing. And one thing must be clearly understood: the Voyagers have not left the solar system. The heliopause is a magnetic boundary, the edge of the solar wind's influence. But the gravitational domain of our star extends enormously further. Roughly 1 trillion icy bodies orbit in the Oort cloud, at distances ranging from a few thousand to 100,000 astronomical units. Voyager 1 will reach the inner edge of the Oort cloud in approximately 300 years. It will not exit the outer edge for another 30,000 years after that. Someone standing in the center of the United States, who takes 3 steps west, has gotten proportionally closer to the Pacific Ocean than Voyager has gotten to the true edge of the solar system. The distances involved are so large that they defeat every intuitive comparison. Light, traveling at 186,000 miles per second, takes more than 23 hours to reach Voyager 1 from Earth. That same light would need roughly 4 years and 3 months to reach the nearest star beyond our own system. The Voyagers, traveling at a tiny fraction of light speed, will need tens of thousands of years to cover distances that light crosses in years. The gap between how fast these machines move and how far the stars are is the gap between human ambition and cosmic reality. And the Voyager mission has made that gap visible for the first time. Carl Sagan and his team had wondered about this gap when designing the Golden Record. They considered the possibility that, just before the Voyagers fell silent in the 2020s or 2030s, one last maneuver might be possible. Each spacecraft still carries hydrazine fuel for attitude control. If, in the final days of communication, engineers emptied the tanks in a single thruster burn, the spacecraft could be nudged onto a trajectory that brings it slightly closer to one of these distant stars. Tens of thousands of years later, the blind, mute machine would drift through the general vicinity of a red dwarf, carrying its golden record through a stellar neighborhood that might, conceivably, contain someone capable of finding it. The idea was never implemented, but the fuel is still there, and the possibility, however remote, has not been formally abandoned. In the vacuum of interstellar space, there is almost nothing to degrade the Voyagers. No atmosphere to create drag or erosion, no moisture to corrode the metal surfaces, no oxygen to rust the joints and connections. The only threats are micrometeorite impacts and the slow bombardment of cosmic rays, and at the particle densities of interstellar space. Both of these processes operate on timescales of hundreds of millions of years. The spacecraft will erode eventually, but the timescale is so long that it makes geological epochs look brief. The aluminum frames will persist, the gold-plated records will remain intact. The scientific instruments, locked in their final positions by frozen actuators, will keep their shape. The thermal blankets may slowly degrade, as cosmic rays break down the molecular bonds in the material, but the structural components underneath will endure. The Voyagers were built to survive the radiation environment of Jupiter, which is vastly more intense than anything they will encounter in the cold stillness between the stars. The golden records are particularly durable. Gold does not tarnish or corrode in vacuum. The etchings on the protective aluminum covers, the symbolic instructions for playing the record, the pulsar map showing Earth's location, all of these will remain legible for hundreds of millions of years. The audio grooves pressed into the copper substrate will survive as well, preserving Bach's Brandenburg Concerto, Beethoven's Fifth Symphony, the sound of a mother greeting her newborn child, and greetings in 55 languages, in a format that any civilization capable of building a phonograph could decode, long after every building on Earth has crumbled to dust, long after every written language has been forgotten, long after the continents have drifted into shapes no living person would recognize, long after the species that built these machines has evolved into something unrecognizable or disappeared entirely. The Voyagers will still be out there, carrying the sounds and images of a world that no longer exists. They may, in the most literal sense, be the last physical evidence that a civilization called humanity ever occupied a small blue planet orbiting an ordinary star in an unremarkable arm of the Milky Way galaxy. Two small machines, drifting in perfect silence through an emptiness that stretches in every direction for light years, carrying golden records that nobody may ever play, headed nowhere in particular, for a period of time that defies every unit of measurement humans have invented to describe duration. The pyramids of Giza are roughly 4,500 years old. The Voyagers will not reach their first stellar neighborhood for 40,000 years. By the time Voyager 2 passes Sirius, nearly 300,000 years will have elapsed, a span of time longer than the entire existence of the human species to date. The machines will outlast everything. They were built to explore a solar system, and they will end up as fossils drifting through a galaxy that may not contain a single descendant of the creatures that built them. Carl Sagan understood this when he helped design the records. He knew the spacecraft might outlast everything. The launching of this bottle into the cosmic ocean, he wrote, says something very hopeful about life on this planet. The hope was never that someone would find the bottle. The hope was in the act of throwing it. Here is what the Voyager journey actually reveals when you follow the full trajectory from launch to silence to eternity. 2 spacecraft were built with 1970s technology, launched during a planetary alignment that will not recur for 176 years, and sent on a tour of the outer solar system that produced more discoveries than any mission before or since. They found active volcanoes on a moon that should have been dead. They found evidence of an ocean beneath the ice of another moon that may harbor life. They photographed storms with winds 8 times faster than the worst hurricanes on Earth. They discovered rings around every giant planet, geysers erupting from surfaces colder than anything terrestrial, and an atmosphere thicker than our own wrapped around a moon smaller than Mercury. They took a photograph of their home planet from 4 billion miles away, a photograph so powerful and so humbling that it changed the way a species thinks about itself and its place in the cosmos. They crossed a boundary no human creation had ever reached, and on the other side, they discovered that the space between the stars hums with a quiet, constant voice that has been playing since before our solar system formed. And now, after all of that, after rewriting the textbooks of planetary science, after capturing the most iconic photograph in human history, after crossing a boundary that no human creation had ever reached, the Voyagers are dying. 4 watts of power drain away every year. The instruments that made those discoveries are being switched off one by one. Within the next decade, both spacecraft will fall silent, and humanity will have no functioning presence beyond the inner solar system. After the silence comes the drifting, the long, cold, infinite drifting, 40,000 years to pass near a red dwarf that will take no notice of them. 300,000 years to drift past the brightest star in our sky, at a distance that makes the encounter meaningless. Millions upon millions of years of cold, dark emptiness, carrying golden records full of whale songs and bark and greetings in languages that were already dying before the Voyagers even launched. The terrifying truth is the scale. After nearly 50 years of continuous travel at 38,000 miles per hour, a velocity that would carry you from New York to Los Angeles in roughly 5 minutes, humanity's farthest creation has barely moved relative to the distances between stars. The numbers lose all meaning at this scale. Miles, kilometers, astronomical units, light years, every unit of measurement becomes insufficient when trying to convey the sheer emptiness that separates one stellar system from the next. The nearest stellar system is still inconceivably far away. The edge of the solar system's gravitational influence is hundreds of times more distant than where the Voyagers sit now. The galaxy is so enormous that the fastest objects our species has ever built are, in cosmic terms, standing perfectly still. And yet these two small machines did something that nothing else in the history of our civilization has ever done. They left. They crossed the boundary. They heard the hum of interstellar space and sent the recording back to us across 15 billion miles. They carried our music and our voices into a silence so vast that the sound will need 40,000 years to reach the nearest neighbor, if it reaches anything at all. The universe is large beyond comprehension, cold beyond endurance, and empty beyond imagination. Two machines the size of a small car, running on less power than a light bulb, carrying the sounds of a world that may not survive long enough to hear back, went further into that darkness than anything our species has ever made. The engineers who built them are mostly gone now. Ed Stone, the project scientist who oversaw the mission for over 50 years, died in 2024 at the age of 88. Many of the original team members have retired. The young graduate students who watched the Jupiter images arrive in 1979 are now in their 70s. A new generation maintains the communication link. People who were not born when the spacecraft launched, working with systems they did not design, keeping alive a connection that crosses 15 billion miles of empty space. The Voyagers are still out there. They are still moving. And for a little while longer, perhaps a few more years, perhaps until the early 2030s, they are still talking to us. Every day the data arrives, traveling for nearly 24 hours at the speed of light, carrying measurements from the farthest laboratory humanity has ever built. Every day could be the last. And every day it is not the last is another day that two small machines, alone in the dark between the stars, remind us what we are capable of when we aim for the edge of everything we know.